So then, welcome back after the lunch break for the third lecture. The third lecture today has the title Multifunctional Materials. I already showed you the applied transducers, so you can have a look afterwards, after the lecture, and we set up a small experiment we will show after the fourth lecture, so in the afternoon. So multifunctional materials, we are now here in the block after lunch. Thereafter we will have a tea break, and then at 4:15 p.m. we will start with our last lecture today. We will look at multifunctional materials, sensing and actuating properties, and also physical properties of the materials. In this lecture we will not go into detail of the physical principle of, for example, piezoceramics. This is in the next lecture. We will look more general on multifunctional materials. So, as in the last lecture, we have again learning objectives. The first learning objective is that you can name characteristics of structural materials, of functional materials, and multifunctional materials, and also differentiate the term. Then you should be able to give examples of actuating and sensing materials. Just name the materials, not their physical mechanisms. You know the most important key parameters of multifunctional materials and also explain their significance. And you can explain structural conformity using the work diagram, which we will introduce in this lecture. And here you can see a piezo composite transducer, a rather thin one, which is applied to this small CFRP beams we have here on the desk. Coming back to the elements of smart structures, we are here at the material level now. So the most basic element, so to say. And first we need a definition, a clarification of the term structural material, because I think outside of smart structures for mechanical engineering, every material or most of the material are used for its structural properties. So structural materials, according to the definition of Xenapius, are primarily characterized by their mechanical properties, stiffness and strength. These materials are passive and not activatable. There's another definition from Baker, who's also from Technological University Braunschweig, and he wrote that materials are often also used in design where their main task is to carry mechanical loads. So materials that are intended primarily to meet these requirements are referred to as structural materials. So structural materials are really the materials to build load-carrying structures and are defined or characterized by their mechanical properties. Functional materials are in general energy transducers. So they transduce different energy forms into each other. And the fundamental forms of these energies are mechanical, thermal, electrical, and magnetic energies. And functional materials can, for example, be transducers which transform mechanical energy into electrical energy, thermal energy into electrical energy, or magnetic energy into mechanical energy. So they convert energy forms between each other. And typical examples are piezoelectric materials. This is also the basis material for the transducers we brought and you will use in the lab. And they convert pressure into charge displacement. You may also know shape memory alloys, which convert heat into a deformation. And magnetostrictive materials, which convert a magnetic field into a deformation. So functional materials, according to Xenapius, are energy converters, which are referred to in the literature as active functional materials. And the basic forms, as mentioned, are of energy are mechanical, thermal, electrical, and magnetic energies. So in the sense Synapius defined the functional materials, these are active functional materials which are activated by environmental conditions. There's again a definition by Baker, who said that any material which is not primarily employed for construction or for load bearing due to its mechanical properties can be described as a functional material. So in his example, he also used copper as an example, which is an electrical conductor like aluminium, and both could also be used for load-bearing structures. So they have different functions, and they are passive materials and not energy transducers, like in the definition of Synapius. So the definitions are not consistent, and we use the definitions in the sense of Synapius in this course. So functional materials, according to Baker, are not necessarily activatable, like the copper conductor. And Baker also does not distinguish between active and passive functional materials, but we do. We use functional materials in the sense of an activatable functional material. There's another point. A functional material is not necessarily multifunctional. So if you have a material which is not for load bearing but delivers a different function, then it's a functional material, but it does not necessarily have to deliver several functions. So functional materials and multifunctional materials are not interchangeable as synonyms. What are then multifunctional materials? Multifunctional materials are characterized by the fact that in addition to properties of a structural material, so primarily load-bearing properties, they have further properties, for example, actuating or sensing properties. And in contrast to discrete functional components we use in mechatronics, for example, they retain their functional properties or their physical effect when they are divided. So it's really a material, not an element. If you cut down a piezoceramic, then it still has its functional or multifunctional properties. And piezoceramics are also a good example for multifunctional materials because they also have an E modulus of around 60 gigapascals, so close to aluminium, and can also be used for load bearing, or they also bear loads. So to sum up these different definitions, structural materials are materials from which components are designed and manufactured. So they cannot be activated, are passive, and primarily characterized by their properties of stiffness and strength. Functional materials fulfill specific function when they are excited or actuated by environmental conditions, like an electrical field, for example, or a magnetic field. And multifunctional materials are characterized by the fact, in addition to the properties of a structural material, so the load-bearing properties, that they exhibit further properties like actuating or sensing properties. And again, in contrast to functional components or functional elements, these multifunctional materials retain their functional properties when they are divided. If you cut a mechatronic actuator in half, then it won't work anymore, and the piezo ceramic would have still its properties even if it's cut in half, for example. So with these multifunctional materials, we can then build up our adaptive lightweight structure. We have the structural material, the load-bearing material, which could be a fiber composite or a metal. And then we add the multifunctional material to it to get a multifunctional structure. And this addition could be due to an application, so you just bond the material or the actuator on the structure, which is the only possibility if you use metals, or you can integrate them if you use fiber composite materials. So with fiber composite materials, the levels of integration, or we can achieve higher levels of integrations like we saw in the last lecture. And here in this example, we have fiber composite structure, CFRP, but the actuators to show them are still applied and not integrated. We will have a lecture on integration, on different ways of integration of these piezoceramic transducers also this week. Who of you is familiar with fiber composites in general? Who has experience with that from lecture or hands-on experience? Okay. You may have also. Yeah. Okay. Yeah, we will have also a quite brief general introduction to fiber composite materials, but not going into detail due to the time constraints. So coming back to energy conversion in ferroelectrics, we have different relations of ferroelectrics among mechanics, electrical, and thermodynamics. And this figure is from Heckmann. And I don't know if you can really read it from behind, but I will go through it. So we have here mechanics characterized by the stress sigma. We have the electricity with the electric field E, and we have the temperature T from thermodynamics. And then we have different relationships between electricity and mechanics. We have the electromechanics. So we have the piezoelectricity and the inverse piezoelectric effect, which connects, for example, the electric field with the elongation or the stress with the polarization of the material. We have a relationship between the electrical field E and the temperature. It's the thermoelectricity with the pyroelectric and the electrocaloric effect, which connects, for example, the electric field with the entropy S. And then we have the relation between mechanics, the mechanical stress sigma, and the temperature, the thermoelasticity, so characterized by the coefficient of thermal expansion, and also several other effects like the piezocaloric or the thermal elongation effect. And since we use electric fields in this lecture, smart structures a lot, we have the quantity or the unity for the electric field is E, and the Young's modulus will be a large epsilon. So I will mention it when it comes up the first time, but in our case, E is not the Young's modulus, but it's the electric field. So examples of sensing materials are piezoelectric ceramics, which could be fibers or thin films. Here we have thin piezoelectric fibers. We also go into detail in, or show briefly how they could be manufactured, and then how you come from a piezoceramic material to the piezocomposite to the piezocomposite actuator or transducer. So this will be a separate lecture. Then we have magnetostrictive materials, which couple magnetic fields with stresses or with deformations. And we have the, here we will not go into detail, and we have electroactive polymers, which we also will have a lecture on. So piezoelectric ceramics, for example, PZT, so lead zirconate titanate, which is the most common material, is a mechanical electrical transducer. So it a mechanical stress induces a charge displacement. This is the effect in this material. The magnetostrictive materials, there we have, for example, nickel or niob, where which is a mechanical magnetic transducer. So under an external load, the strain generates a magnetic induction. And then we have the electroactive polymers, where we also have some different subgroups we will then have a look at in the lecture. But an example is PVDF. This is the same material the multifunctional elements in the adhesive bond line are made from. And PVDF is also a mechanical electrical transducer like the piezo ceramic, and it also transduces mechanical stress into charge or ion transport. Then, if we use the inverse effect, we can also use these materials or some of these materials as actuating materials. There we have again piezo ceramics. When we use them as actuators, we have maybe larger parts or thicker parts. So we have not only fibers and films, but also stacks and plates. We still have the magnetostrictive materials. We have magnetorheological and electrorheological fluids and shape memory alloys, you may all know. So again, piezo ceramics used as actuating material. Then we use again it as an electromechanical transducer. But here the electric field leads to a mechanical deformation, so we can control the deformation of the material with an electric field. At the magnetostrictive materials, we can use a magnetic field to produce a mechanical strain, so also a deformation. At the magnetorheological and electrorheological fluids, there we can use a magnetic or an electric field and produce a change in the viscosity of the fluid. So the first adaptable suspension systems of cars were made with these electrorheological fluids. So you could change the electric field, and then you can change the viscosity, for example, in a damper to improve ride comfort in cars. And the shape memory alloys, there we have a thermomechanical transducer. When we heat it up, a deformed alloy leads to a mechanical shape recovery. So we get the memorized shape of the alloy back when we heat it up. We also do not go into detail into shape memory alloys in this lecture. So we will really focus on piezo ceramics and on the electroactive polymers here. So as a nice overview slide for multifunctional materials, we have the different effects: electromechanical transducers, magnetomechanical transducers, and thermomechanical transducers. So an electric field, temperature change, or magnetic field leads to reversible change in geometry, stiffness, or viscosity, like in the magnetorheological fluids. And common example materials are piezoelectric ceramics, piezoelectric polymers like PVDF, electrorheological fluids, electroactive polymers, carbon nanotubes actuators as well. We could not only have shape memory alloys, but also shape memory polymers and magnetostrictive and magnetorheological fluids. And also there are some magnetic shape memory alloys. So coming now to the sensing and actuating properties, to the fundamental principles, and what we want to have is, if a material acts as a sensor, it should convert a physical quantity independent of other external influences into a signal, usually an electrical signal. And by doing so, we have sensing functional materials which could sense motion quantities or displacement or strains into an electrical signal, or thermal changes into an electrical signal. They transform the input quantities for the adaptive system. So we use the sensing properties to, for example, measure the disturbance and feed this signal into a controller. What we like to have is that we have an input quantity xi, which is converted via a unique functional relationship into the output quantity x0. So here it is. It should only one x0, but yeah, you can cross that out later on. So we would like to have this kind of behavior. We have an input variable, for example, the strain xi, and an output variable, the charge, and it should be really defined so that we have a clear definition. This strain corresponds to this charge or electric signal. In reality, we have more like this behavior. We have kind of hysteresis, which leads to not a clear definition. So we have not a unique functional relationship, because if we look here at for example, one defined strain, depending on the history, we could have this electrical output or this electrical output. Do you have ideas where these, let's say, imperfect behavior comes from? Sorry? Stresses, yeah. For example, stresses. Any other? Okay. So we will get more into detail in the principles, but you can say that we have a nonlinear transduction. So in general, the transduction is not linear. We have cross sensitivity. So if we have other fields, like in an electric mechanical converter or transducer, it could be sensitive to, for example, magnetic fields, and then we have some influences. We have some kind of noise and also sensitivity drifts if we use the sensor over a long time without recalibrating it. So the same we would like to have for an actuating material, where we convert a control signal, which is usually an electrical signal, into a physical quantity independent of other external influences, so independent of other cross sensitivities, for example. So we would like to convert electrical signals into motion quantities. And this is also what you will do in the lab. You will give with a function generator an electrical control signal, which goes into a high voltage amplifier and then produces the electric field, and this then leads to a deformation of a piezo ceramic. So this you will try out hands-on. And with this, we define the response of the adaptive system. So this is if we have the disturbance signal and the controller, then we use the actuating material to, for example, bring the satellite reflector back in its original shape, where we want to have it to have a good transmission of the signal. So in here again, the input variable now is a voltage, and the output variable would be, for example, a strain. And this is the behavior we'd like to have. In reality, we have more a behavior like this with an hysteresis and some other effects. And again, we have a non-linear transduction, cross-sensitivity, and also sensitivity drift, which are all disturbance factors. So now we are coming to the physical properties, and for this I try to sketch something on the slides. So maybe we start with the free displacement. So an energy input, we are now on the actuating of the usage in terms of actuating of the material. So an energy input induces a change in length of the multifunctional material, for example, the piezo ceramic material. And and we assume that we have no external constraint, so it can freely move the material or the piezoceramic, and the free displacement U0 is then the maximum unconstrained change in length of a multifunctional material achievable through energy input. So we have here this this electrical transducer, and here it's original length L0, and then if we increase the potential energy by supplying, for example, electric energy through an electrical field, then this transducer will extend by U0, which is shown here, so it elongates quite a bit, and we have no external constraints. So this is really the free displacement, the maximum the multifunctional material is capable of doing. And if we look at the diagram, for example, the potential energy or the energy over the potential energy, so the input energy, maybe we write here input, then you will get a maximum potential energy. And if you look at the similar diagram where we have here the electric field, then there is a maximum value of the electric field E max, and this corresponds to the maximum free displacement. So we have the displacement U, here's the free displacement U0, and if we would increase the electric field more, the displacement would not further increase. And if we, let's say, have the electric field, an electric field which is too large, then it would also destroy the piezoceramic effect, and we lose the polarization or have an electrical breakdown. So I will then next we have the free strain, epsilon 0, which is closely related to the free displacement. So we have the maximum unconstrained relative change in length. We just divide the free displacement by the initial length L0, and then we get the free strain epsilon 0. Then our next quantity is the blocking force and the blocking stress. We define it as FB, the blocking force, and this is defined as the force you need to push back the multifunctional materials to its original length L0. So if you first measure the free displacement without any constraints, then you have this transducer, for example, this cylindrical one, extended to its maximum, L0 plus U0. And if you then push it back to L0 again, while the electric field is still applied to the transducer, then you get the blocking force. So it's the force the actuator or the material can apply at the maximum. So is it clear how the blocking force? Yeah.
Why only length extension happening? Contraction also some materials.
Mm-hmm. Depends on the direction of the electrical field. So you can, but in
it is neutral.
Hmm?
It is neutral.
Yeah.
Composite material, neutral one.
It's in so our, let's say, basic principles here, we also only have the piezoceramic material. Yeah. So it's from the idea, if you just have a block of the piezoelectric material and maybe some electrodes to apply the electric field, and then in the first step, you will measure the free displacement, just applying a maximum electric field and see how it extends, and measure this U0. And then in the next step, you would push it back to U0 while maintaining the electrical field. And this is then the blocking force. This is the maximum force you can apply with the actuator without any movement. And you will also do this in the first lab experiment on your own. So we will, after the next lecture, we will show something with this setup, but you will use the setup then to really measure the free displacement and also some forces. Yep. Sorry? Yeah, yeah. So the epsilon, you mean? So the blocking force, you can also say that the blocking force is the cross section A times the blocking stress sigma B, and here sigma B you can also state as epsilon A, which is now our Young's modulus in this lecture because E is the electric field, and you have then the strain U0 divided by L0. And we can also define a spring stiffness of the multifunctional material Ka, which is the cross section times the Young's modulus divided by the initial length, and therefore you can relate blocking force and free displacement with this spring stiffness Fb equals spring stiffness Ka times U0. Okay. So blocking stress, we have already defined on the slide before, but just for completion. So blocking stress is sigma B, is defined as the stress that occurs in the material when the maximum active strain is prevented or blocked. So if we could apply the maximum strain, but we block it with an external force, then we get the blocking stress, the maximum stress. And yeah, it's for linear elastic material. Sorry, we have just Hooke's equation. So sigma B blocking stress is Young's modulus of the actuator times the free strain in this case. So now we can build up a relationship between active strain and external load. So if we try to maybe point it that way. If we have an external load as well as a strain due to energy input, then we could come up with these functional relationship. We have this strain epsilon z, which is the total strain, and it's made from the sum of the free strain plus the overall stress divided by the modulus of the actuating material. And we can also put in that our free strain is the free displacement by the initial length. And we could also define that the overall stress in the material is the force Fa, so not the blocking force. This is Fb, but this is Fa, just an external force acting on the transducer divided by the cross-section A. And then we could also write it down in force displacement notation. So we have the total displacement U is U0 minus Fa divided by the spring stiffness Ka, which we have already defined. And with that, we can build up a so-called work diagram. So here the work diagram, which you will also generate, or which is an outcome of the first lab. So in the work diagram, you have here the displacement of the actuator, and you have here the external or the force axis on the x-axis, and then you can put in two quantities. You have the free displacement, which is here, which is the displacement without a force. So it's here when the force is 0, you have here the free displacement u0. And the other way around, we have here the blocking force, which is Fb. And the blocking force is defined as the force we need to push back the actuator to its original length. So we have no displacement u. And therefore here we have this on the y-axis 0, here the blocking force. And if we connect these 2 points, we will get this line, and the slope of this line is the spring stiffness of the actuating material. And this we call work diagram, and you will in the lab measure this point and also several other points on this line, and with this then you can construct the work diagram from the experiment. Fb is the blocking force. So Fb is the blocking force, which is the force you need to if you apply the electric field to the piezoceramic, it elongates, and if you push it back to its original length, then the force you need for this is the blocking force.
So electric field, like it will be active during the pushing back?
Yeah. Otherwise, if you remove the electric field, then it will the transducer will shorten again. So then the elongation is just due to the active electric field. So you have the active electric field and then push it back to L0.
Is there any permanent set in this case? Will happen like a normal physical application?
You mean a static displacement you can?
After some value of Emax, it will set into some extent. Suppose 5 centimeters, like 0.005 will stay there, and remaining may come down.
Yeah, I think you will have some kind of drift over time, so it will not be perfectly back to L0. But I have no numbers in mind how much it is, so how the drift over time is then. Yeah. Okay, then we go to the next slide. Again, so now our model for the integration into a structural model is that maybe again this pointer is that if you integrate this multifunctional material, piezoceramic transducer, for example, in a surrounding structure, which could be CFRP, but it's just a simple model, then and supply energy, then the actuator will work against the stiffness of the structure, right? So if the actuator wants to deform, it has to deform also the surrounding structure. And a model for this is the model we already used for the transducer, for the multifunctional material, which with its spring stiffness Ka. And now we have, in addition, a spring for the structure with the spring stiffness Ks, and they are connected so that they have the same displacement overall. And we have here force Fa acting on the actuator and the force Fs acting on the structure. So and now we again have the force displacement of the actuator, which is u0 minus the force acting on the actuator, which is dependent on u, divided by Ka. So this is the equation to describe this line. Maybe I do it again. The equation to describe this line. So if the force is here, if this would be 0, then we just have u0 and here at this point. And then we have the spring force of the structural connection. So we can say Ks times U, so the spring stiffness multiplied by the displacement is Fs. Here's a small mistake on the slide. This has to be Fs. And then we can also come up with a relation between, so no, first this equation, so Fs independent of U equals Ks times U, and this is this line here with the slope Ks. So here, if you have no displacement, if U equals 0, then Fs would also be 0. You are here at this point. Now we can define a stiffness ratio between the actuator stiffness and structural stiffness. So alpha K is Ks divided by Ka. And then we can use this relationship and equation 8 to formulate this equation. So the overall displacement is the free displacement U0 times 1 divided by 1 plus alpha K. So this is then the actuator displacement in total. And with this coefficient of or the stiffness ratio, we can see the influence of the stiffness of the structure compared to the stiffness of the actuating material. Now it's working. And now we can also, did I miss the slide? No. I missed something. So if we look at this diagram here again, then we have the both lines for the force displacement behavior of the actuator and the structure, and they meet here at this point. And the area under this curve, this is the work which can be performed by the actuator, which is integrated into the structure. So it can only, let's say, deform up to this point, because otherwise the actuator is not strong enough to deform the structure. And this performed work can also be written as WA equals half or 0.5 times Ks times U squared. So this is this area. And you can also express this in terms of the stiffness ratios of the material, so with the alpha K again, and then you have this equation. Then we have an equation for the work capacity or the maximum work performed, which depends on properties of the actuator, the spring stiffness of the actuator, and the free displacement, and the stiffness ratio alpha K between the structure and the actuator. And the part in front we could also name as VWA with an WA with an overline. So, and if we then go to the next slide, we can have a look at this diagram, which shows the this one part of the product here. So the square needs to be outside of the brackets, independent of alpha K. And what you can see is that at this point, 10 to the power of 0, so alpha K 1, there we have this WA overline at a maximum here of about 0.25 or 1/4. and this gives us the maximum work capacity of an integrated actuator. And now we can replace this expression here with this maximum value, which is 1/4, and then we have this expression again with 1/4 in front, so 1/8 times Ka times U0 squared is the maximum work capacity you can perform when the stiffness ratio between the actuator and the structure is 1. So maximum structural conformity is achieved when the structure and the actuator have the same stiffness. Then you can perform the maximum, then the actuator can perform the maximum work in the structure. And this is the goal, because then you have the most efficient system, so to say. And this is also shown here. So with an negative sign, you have the same stiffnesses in this diagram of Ka and Ks, but with changed signs. So structural conformity is achieved when stiffnesses of actuator and structure are the same. Yeah. Mm-hmm. Sorry, yeah. Maybe the answer comes on the next slide. I will show it and then I come back to you again. Or maybe it's, oh, where's this slide I'm looking for. Now we have this work diagram for different structural stiffnesses, so different structural materials. And the actuator always has the same spring stiffness. Here in the middle, we have alpha K equals 1. This is the case we saw on the last slide. And in this case, here on the left-hand side, Ks is smaller than Ka. So the actuator is stiffer than the surrounding structure. Here we have axis changed, like let's say we are used to. So usually here is the force and here's the displacement, and therefore a higher slope would be a stiffer material. But since we changed axis, now Ks with a higher slope here means we have a less stiff surrounding structure. And then you can see that the point where the two lines meet is here. So we can have higher displacements. So here we in the integrated structure, the maximum displacement is at this point, and this is the maximum force the actuator can apply. And if the structure is less stiff than the actuator, we can achieve higher maximum displacements, but far lower maximum forces. And therefore the area here under the curve is smaller than in the optimal case where the stiffnesses agree. So we can, even if we have the same actuator, when it's integrated into a less stiff structure, we can perform less work with this actuator. So you can, maybe a rather simple model is if you have, for example, two hands and you push one hand, which is the actuator, against the structure, then you can move it with some pressure. In this case here, where the structure is less stiff, you push, for example, against air. So you can make large displacements, but you can not bring up any force to it. And the other case, the other way around, where the actuator is less stiff than the structure. So we have a really stiff structure. This is the case here. There you have a very low maximum displacement, but you can nearly achieve the blocking force. But also the work capacity, again, the area under this curve is far lower than in the case of structural conformity. And the model for this would be if you push your hand against a wall, and the wall is the structure, it's very stiff against your actuator, then you can achieve high forces, but the wall won't move. So therefore, so even if you have the same actuator, it depends on the surrounding structure how much work you can perform. And this concept of structural conformity can also be extended to functional conformity when we have additional properties of sensing and actuation harmonized with the properties of the design. If you think back of the multifunctional adhesive bond line, if we integrate these elements as a sensor, then the sensing function may be optimal, but if we use this element also as crack stopping feature, then maybe the best position of these elements is another position than for sensing, and this would be functional conformity, to find the right balance of function and positioning of the elements in the structure. So then we have some additional work and performance metrics. So we have the work capacity. We'll go back to this presenter. We have the work capacity, the maximum work capacity defined when we reach structural conformity. Stiffnesses between structure and actuator agree. And if we divided by the volume, so the volume specific work capacity, cross section times length is the volume. Then we have the energy density of this structural system, which can be the modulus times the displacement epsilon 0 squared 1/8 again. We also have power figures of merit. So if we have the density specific energy density, so energy density is WE, and if we have it divided by the density, then we have the specific energy density WS. And for dynamic processes, we have also a specific power WL, which is WS, the energy density, times the frequency. But we will not look much into dynamic processes in this lecture. So in the lab, everything we do is more or less static. So to give an overview for the learning goals about the characteristic parameters of the actuator material, we have the blocking force, FB. We have the free displacement, U0. We have the free strain, which is epsilon 0. Then the blocking stress, which corresponds to the blocking force. The maximum work capacity, WA, which can be at maximum 1/8 times spring stiffness of the actuating material times U0 squared. And we have the energy density. So with that, we come to the summary of this lecture. So functional materials are energy transducer. Multifunctional materials are structural materials which also have actuating and sensing properties, like for example piezoceramics. We have had examples of sensing and actuating materials, electric field, or transducers which use the electric field, piezoceramics. For temperature changes, we have the shape memory alloys, and magnetic field, for example, magnetostrictive materials. When we use them for sensing, we try to convert changes in kinematics or thermal changes into electrical signals. And for actuating, the other way around, we have electric control signals, which we want to convert into motion quantities. This transduction is not perfect. We have disturbance factors like drift or hysteresis effects. And we introduced some key parameters like blocking force, blocking stress, free displacement, free strain, work capacity, and specific work capacity. And structural conformity is reached when the stiffness of the structure, the Young's modulus, meets the stiffness of the actuator. So do you have questions on this? Yep. So their shape memory alloys are thermal mechanical transducers, where you can save and memorize a shape, and if you heat it up again, so you bring it in shape, cool it down, and if you heat it up again, then it will get to its original shape. But it's not part of this GIAN short course due to time constraints. Okay, I think it may get more clear in the first lab when you do the first lab experiment where you will measure the free displacement, also the blocking force on your own, and construct this work diagram.